Welcome back. We will continue our discussion with soft lithography, and we had been talking about capillary force lithography when we finished our last lecture. So, we will continue with CFL, but what I will introduce you right now, or what I will take a couple of minutes to highlight to you, that right now we have up till now we have learned quite a few patterning methods, some of which fall under the category of classical soft lithography, and some of the methods, at least 3 of the methods that you should be able to recall are mimic, samim and CFL. In addition, we have also learned nano imprint lithography, which due to historical perspective, because it was discovered by Stephen Chow at Minnesota, not by Whitesides. It uses a rigid stamp. If you remember our discussion, so historically it was not part of the soft lithography group, but many people now consider that NIL is also one of the soft lithography methods. Without going into that argument, really what we can definitely conclusively conclude is that both NIL as well as these other soft lithographic techniques, they fall into the category of non-photolithographic techniques for patterning, and the generic nature of the techniques make these methods rather useful or easy to implement for polymers or soft materials, and you do not require complex materials like photoactive photoresists or things like that. They can be very easily used for simple straight chain polymers with a little bit of tuning of glass transition temperature to either room temperature or by a little bit of heating or things like that. So, that way if you now contrast the methodologies we have talked about, nano imprint lithography as well as mimic, samim and CFL, and you compare it with what we have already discussed a few lectures back about photolithography, you can immediately understand the processing steps as well as the hardware requirement in these methods is much less cumbersome and less complicated as compared to what you would require in photolithography. So, that way these methods are really very simple. Photolithography, of course, you have optical exposure, then you have several developing stage, then you have doping, etc., etc. So, that way these methods are much stable, much easy to implement, and you require much less infrastructural requirement. Therefore, these structures also, the patterns made out of these techniques can be fabricated at a much lower cost, which we have talked in probably the first couple of lectures of this course itself, that which makes these methods ideally suited for bulk nano application, where you need high fidelity large area structures in large numbers rather than maintaining absolute critical requirement and in terms of dimensional tolerance as is necessary in microelectronics. However, if you have carefully been following the lectures, you might have noticed one specific thing, and that issue is that in all these methods we have mentioned so far, you are actually producing by somewhat different techniques or mechanisms or method or protocol a perfect negative replica of an original stamp or a mold. In soft lithography literature, you refer the original thing as a stamp. In nano imprint lithography literature, you refer to it as a mold. But reality is, irrespective of that, what you are always able to achieve is a negative replica. Therefore, one of the limitation, and then comes the question, how does or where does one produce this original mold or stamp? In nano imprint lithography group of methods, you know that you require a rigid silicon master, which often is fabricated by photolithography itself or some other high end lithography technique. In soft lithography group of methods, in most cases you use a flexible PDMS stamp, but that PDMS stamp has to be made by, or is generally made in most cases by, replica molding, which is another soft lithography technique itself, is the simplest one I would say, by replica molding against a lithographically fabricated master. So, what are the limitations now? The limitations of soft lithography that emerges, including nano imprint lithography, that they require a primary structure which contains a perfect negative replica of the desired structure. Okay, that is important. The structure you want to make, it contains a negative replica of that. That is the stamp, because ultimately what you are making by any one of these methods is a negative replica of what you already have in your master or mold or wherever. And to produce this, you have to rely on some other lithography technique. So, that way soft lithography is to a large extent dependent on some other lithography method. The other critical issue that emerges, so even if you start sort of producing, let us say in most soft lithography group of methods, since you use a flexible stamp, so once you have one lithographically fabricated master, you can then go on producing it by replica molding, as we have sort of make multiple. This is a method by which you can make multiple copies, I can say, like a Xerox machine maybe, of the original pattern. Okay. But then again you have to understand one specific thing. For every design of structure you want to make, suppose you want to make these two type of structures by soft lithography, let us say this has a periodicity of lambda 1, line width of LP1 and height of H1 versus so generically both of them are, let us say, gratings, but you would be needing two different stamps to make these two structures. So, originally somewhere down the line you need to have two photolithographically or some other made by some other lithography, two distinct original masters, which then you can go on producing or mass produce following any one of the soft lithography techniques. So, that way so you can understand that since this original master have to be fabricated by photolithography or some other high end lithography, it is costly, and every new design you want to make would essentially require or will force you to get an originally fabricated stamp. And the other thing to realize is that we have shown some structures which are simple grating structures. The cost of a stamp, a lithographically fabricated stamp, sort of exponentially increases with two things. Number one is the geometrical complexity. Of the features, and number two is the dimension of the features. By geometrical complexity we mean that the simplest structures are probably the gratings. More complex structures like ordered array of something like this, 2D pillars or rectangular pillars or something, well then it becomes more and more complex. Similarly, the smaller the feature size is, it becomes more and more difficult to fabricate. Let us say if you want to make simple gratings with 5 micron line width vis-a-vis with 50 nanometer line width, maybe you will be ending up paying 10 times higher price for in the latter case. Okay. So, the third aspect also that sometimes really affects the cost of a lithographically fabricated stamp or a structure is how much amount of area you want it. because photolithography is a parallel process, but many of the direct write methods like electron beam lithography, focused ion beam, we haven't covered these techniques in detail, but you can always look into the literature and find out what they are. So, they are serial writing methods. So, creating these structures, they can produce features with extremely low lateral resolution down to let us say 20 nanometer. But if you want to have these structures over a few centimeter square area, that might actually take few days to write the whole area, because the tip has to physically raster at every location, go come back and dislodge the material or burn off the material to create the structure. Okay. So, the larger area is requirement you have for your original stamp, that is also going to sort of increase the cost of your hardware or the stamp. So, therefore, there has been significant research particularly in the area of soft lithography, is what is known as beyond the master patterning. What it means is that you produce final structures which are not only a perfect negative replica of your stamp or master, but it can be more complex patterns. Okay. It can be different in the periodicity, it can be different in line width, it can be geometrically different, something like that. So, then what happens is that you might be having a simple stamp, let us say you have a grating, and the idea is that using a simple grating stamp, can you make structures which are let us say have 2D complex order. So, that would be very, very interesting, and significant amount of research is actually aimed at those directions recently. We I mean, as I have told right at the beginning, that the whole business of soft lithography, patterning, it is an extremely advanced area. So, lot of developments also take place even now. So, every new issue of many of the top notch journals, you find newer techniques which are coming up. But one has to realize that most of these so called new methods are essentially nice extension I would say of majority of the existing techniques. So, it is not possible in a course to cover all the methods that are available, but to give you an idea about how this beyond the master patterning concept can be implemented, I have picked up a few case studies which are all sort of came into existence in the last 5 to 10 years to impress upon you how with a simple stamp, let us say, you can go on creating more complex structure which can have significantly higher degree of complexity and can be used in other higher end functionalities. So, capillary force lithography had been one of the major techniques which offers extreme flexibility to the user in terms of the fact that you can go on making complex structures using simple stamps. So, some of such developments we will discuss. One of the developments is one of the methods that in this regard that came was actually to use 2 molds of stamps by CFL. So, what you do, you first generate a negative replica of your first mold by CFL. So, you had taken a polymer film usual, you have imprinted it or performed capillary force lithography with a grating stamp to obtain a perfect negative replica. So, this I guess with the level of understanding you have, it is easy for you to understand how this can be implemented. So, all you need is a stamp, the walls of which are preferentially wetted by the polymer, which is in either heated or exposed to solvent vapor, so that it is in a liquid stage, and you can simply get a grading structure. If you remember carefully, the pattern replication took place due to confined capillary dynamics, that is capillary driven flow of the polymer along the stamp walls, or in other words, this flow was possible only over the areas where the stamp was in conformal contact with the film surface. Now, in this approach, one of the easiest things that can be done is that once you have a patterned film. So, this is all that polymer, but now it contains a negative replica of the first grading. What about this? You simply place another grating, maybe the same grating with the same geometry at some angle with the already created structures. So, now what happens, what you can understand if we take a detailed view of one replicated structure, let us say. So, this is one CFL structure and let us say we take a cross section at this particular plane. So, here is the second grating, that is paste. So, what you can immediately understand, so this is the structured polymer film now. So, the second grating is now in contact with the patterned film, not all along its length, but only at these locations. Over these locations where the raised portion or the protrusions of the second grating. So, these are protrusions of the second grating. So, this grating you go and place here. So, the protrusions of the second grating are in contact with the pre-patterned film, or the, let me write it down. So, the protrusions are, or grating have spatially varying contact with the first with the imprinted film. Or in other words, you can see that it is only over these specific areas where the protrusions are in contact with the already imprinted film, and over these areas there is no contact. So, here over these areas again there will be a capillary driven flow, which will be doing the second mold filling, but below this zone, since the protrusion or the higher zones or the hills on the patterned film are not in contact with the protrusions of the second grating, there will be no flow. I hope it is clear to you. The way the second grating is placed on the pre-patterned stamp. So, or to make it even simpler, we take a first grating, we create a perfect negative replica of that first grating on the surface of a polymer thin film by capillary force lithography, and then we take a second grating and place it with its protrusion facing towards the patterned film in such a fashion, so that the direction of the stripes on the film of the pre-patterned film and the directions of the stripes of the grating are at 90° with each other. What this results is in a spatial variation in the extent of contact between the second grating stamp and the pre-patterned film surface. So, you can see that there is going to be spatial variation in terms of the contact. So, you have contact over here, you have contact over here, but no contact over these zones. And therefore, if you again allow capillary force lithography or capillary driven flow to take place, the mold filling will only occur over the areas where the second grating stamp is in contact with the patterned bottom layer film. So, what this will imply that this will result in some structures like this. So, you can immediately understand that if I mark, this is the same zone 1 in this particular picture, where you have a second capillary rise below the second grating, and here over let us say zone 3, the stamp and the pre-patterned film, there was no direct contact, and therefore, no pattern replication has resulted over this zone due to the second stamp. So, therefore, what the structure you see now has a 2D order, but what is the real novelty behind this approach? That though you have created a pattern which has 2D order, you have not used a stamp with complex 2D features. Okay. As we have already mentioned that a stamp with complex 2D features would be more expensive, as it will be more difficult to fabricate either photolithographically or by any other high end lithography technique. Instead of that, you have used, all you have done is to use two grating stamps in a slightly clever fashion. So, you first used a grating stamp to generate a CFL negative replica, and then placed another grating stamp on that patterned film at an angle where the stripes were not parallel, they made some angle with each other. It can be 90°, it can be some other angle to generate these type of structures. So, all you are doing that you are varying or controlling the extent of spatial contact between the second stamp and the patterned film, second stamp and the. So, this is an example by which you can use CFL or other methods also, but CFL is very simple to handle in this way, because if you compare it with the other methods, what you have to understand that in CFL you are not bringing in any solvent. So, same thing can also be done with nano imprint lithography. You can do perform a second embossing after an already existing structure, but that has also been done. It is not that it has not been done, but CFL has its unique advantage in the fact that compared to SAMIM or micromolding in capillaries, you do not bring in any solvent, because the moment you bring in solvent, what might happen during the second imprinting step, the solvent might actually distort the first structure, or the structure originated from the first imprinting, and therefore, a technique like mimic or even SAMIM might be pretty difficult to use in this mode to generate beyond the master structures. The other approach, which is pretty similar to this one, but which we did recently and can also be regarded as a nice technique for making more complex structures in by using simple stamp or simple hardware, is to use not to use two gratings as stamps, but to use a one grating stamp and the other grating as a substrate. So, this is now interesting. In all the methods we have been talking for the last few classes now, they use very thin polymer films. Okay. So, we had talked while talking about photolithography that one of the preferred method, particularly with polymers, for making thin films is the method of spin coating. Okay. So, in all the methods we have discussed so far, this thin film was deposited on a flat surface or flat substrate. So, if you remember the basic methodology of spin coating, you dispensed a polymer solution on a flat substrate which was held on a chuck by means of vacuum or other holding devices, and then a high RPM was given. So, it started to rotate, and this centripetal force sort of allowed the solution to spread uniformly over the entire film surface, and simultaneously the solvent also evaporated away, leaving behind the solute, which is nothing but the polymer on the film surface, resulting in ultra thin films. And I think I have also mentioned by this method of spin coating, it is pretty easily possible to fabricate or generate polymer thin films, defect free polymer thin films with very low very low thickness, which can be as low as 15 to 20 nanometer. Spin coating one can also use for making structures which are, let us say, few hundred nanometer thick. For thicker films, spin coating can still be implemented, and industrially it is also implemented, but there is another nice technique that sort of can easily result in few hundred nanometer to few micron thick films, which is known as a dip coating. But for the time being, we will keep our discussion limited to spin coating. So, in this particular, all this CFL, SAMIM, mimic, all this we have implicitly assumed that we understand spin coating, and the thin film we have been talking about have been spin coated. Now, in this particular method or technique we are going to discuss, we take a grating stamp and a grating substrate. So, now the difference is that instead of coating the polymer on a flat substrate, which we have been doing so far, we now are going to coat the film itself on topographically patterned substrate, which is let us say a grating. So, this is now your substrate. So, this is where the problem statement lies now. So, you are going to spin coat on a topographically patterned substrate, which let us say is of the order of like a grating. So, what would you expect? You would probably expect that if your polymer concentration is too low, you will not even get a continuous film. You would probably expect that your polymer will get deposited within the groups if the polymer concentration is very, very low. So, for it will get deposited within the groups, and if your polymer concentration is high enough, probably you will get a film which is fully covered, but still you have an undulating top surface, and the undulations are likely to be so film with undulating. So, this is how the film should look like. And if your film is very, very thick as compared to the depth of your surface features, then maybe you will again have a film which is nearly flat. So, flat film is thick. Okay. So, this is the general notion we had, and so eventually in this case what would happen is that once you get to this configuration, let us say, then if you now place a stamp which is at a direction or let us say the grating is perpendicular to this direction of the undulations. So, the film would be looking after coating would be looking something like this, and so this is the substrate and this is the film with the undulating top surface. So, now if you place the stamp like this, well, you are essentially back to the same geometry now. You again have a spatial variation in the extent of contact between the film surface and the grating stamp. So, over these zones there will be contact and over the other zones there will be no contact, and therefore, in this process it becomes possible to use a grating stamp and a grating substrate to generate structures like this or this with square pillars. This is interesting to note is this is not on a polymer, but this is on a silica and silica titania sol gel film that we made all these structures. By varying the initial thickness as well as the geometry of the stamp and the substrate, it now becomes possible to tailor the exact feature size also. This is the intention is to give you some sort of an idea. So, I do not have any intention of going into a great amount of detail, but one thing is that this mechanism what people thinks is based on this fact that if you have a reasonably thick film, then you would be having a undulating film surface with the undulations where the undulations are in phase with the substrate pattern. But very recently, so if you have been doing an atomic force microscope of the substrate Incidentally, we will take up atomic force microscope as our next topic. As soon as we finish soft lithography, I will give you some basic idea about how an atomic force microscope or an AFM works, so that you understand what you see, how it is correlated to the surface structures. So, you do an AFM of the substrate, you get a structure like this. You get an AFM, so you do the spin coating, and then you, so this is the AFM of the coated film. So, if you superimpose the two, I do not think many of you have a doubt that probably this is how the thing is arranged. Okay. So, you have an undulating top surface where the periodicity of the undulations. So, important thing to note is periodicity of undulations matches the periodicity of the substrate. The amplitude of the undulations, here you can see it is 40 nanometer is the maximum height, here you can see the maximum height is 120 nanometer. So, the undulations, this is the first thing to note. The second thing to note is undulations of the amplitude of the surface undulation, sorry. The amplitude the substrate structures. Very recently, it has been shown that this configuration is valid only when the substrate is completely wettable by the solvent. So, in phase this in phase I will highlight, this is important here, because you get an undulating structure anyway. You get an in phase undulating structure only when the substrate material is completely wetted by the solvent used for spin coating the film or the polymer onto it. This is an important revelation. I will skip all these details. So, this is a surface which was, so this film has been coated, the film which has been coated is a polystyrene film. So, it is a PS film coated from a solution in toluene . So, this is a situation where the substrate was completely wetted. Completely wetted by the solvent, that is by toluene. And it is a clever atomic force microscope image where you can see the substrate. So, this part is the bare substrate and this part is the film. So, you can see that the film surface is also undulated just like the substrate, but the film undulation and the film undulations are in phase with the substrate pattern. So, this I will highlight as the in phase structures. Okay. However, when the substrate is partially wetted, so that is the solvent makes a finite contact angle. By partial wetting, we mean that the solvent makes a finite contact angle with the substrate. Then what happens is, due to intrinsic or in situ dewetting, and this is another word which we will talk in very great detail in one of our in some of our subsequent lectures. So, for the time being, please keep this keyword in mind due to in situ dewetting, but I will skip going into the details right now, because we will be talking about dewetting in much greater detail. But what you can see very clearly over this particular zone, that the undulations on the surface of the intact film. So, this is the undulation, here you can see a hump, here you can see a hump, but this hump sits over a substrate valley. So, here the final morphology indeed resembled what we anticipated. However, here the result is slightly counterintuitive. So, you get a structure like this. So, the only difference is the dispense polymer concentration is the same. So, I would say this is the out of phase structure, this is in phase structure. Okay. So, the only difference between the two cases where the wettability of the substrate. So, in this case, this was a partially wettable substrate, I write it as PW. This case it was a completely wettable substrate depending on CW. So, the reason I highlighted this particular finding is that now when you try to place a second stamp on a film with an undulating top surface, it becomes also important to understand whether this is the geometry or the undulations or the higher locations on the film surface are actually sitting on the substrate valleys. So, the other possibility can be the film is like this. Okay. So, this is very very important, and this will also affect the final morphology of the final structures. But depending, so we have already shown two examples. I mean, this is one, I would say, a fundamental understanding about spin coating on a topographically patterned substrate. And in addition to that, last couple of examples we have already shown that it indeed becomes possible to achieve beyond the master patterning or implement beyond the master patterning concepts. Two examples we have picked up is both of them are, so far we have limited our discussion or kept our discussion limited to CFL based techniques or capillary force lithography based techniques. And the first approach we showed was the use of two stamps or two masters, each having a grating geometry. First one is used to generate a negative replica of the stamp pattern, and then the second stamp is placed on that patterned film at 90 degree or at right angles to the first set of structure. The second example that we have picked up is instead of using two gratings as stamps, we use one of the gratings as a stamp and the other one as a substrate. So, we had to address the issue of direct spin coating or coating a film onto a topographically structured surface, and in this case it was a grating. And in the process I introduced you to something that is a little counterintuitive, because one would invariably think that if you are coating on a topographically patterned substrate and if your film thickness is adequately higher, then you will always get a film which might have an undulating top surface, but the surface undulations will always be in phase with the substrate pattern. But I showed to you that it has been very recently understood, and this is, I go on telling you that this area is still very active. So, this whole understanding came in 2000, as late as in 2012, where people realized for the first time that the structures can be in phase or can be out of phase depending on the wettability of the substrate you are using with respect to the solvent of the polymer. So, what happens is as you spin coat, there is a significant evaporation of the polymer solution. The polymer remains back on the substrate and the solvent evaporates away. So, as the solvent evaporates, the thickness of the solvent film. So, I would say this is the solvent rich film, which contains. So, initially let us say it is like this, this is on the substrate, this is on the substrate, and then there is evaporation, and gradually there is thinning of this solvent rich film during the process of spin coating itself. And once so this layer has now become thin, but still it is rich in solvent. So, its entire hydrodynamics is governed by the hydrodynamics of the solvent, that is the wettability of the substrate by the solvent, and all these things are still dominant. So, now if you have a substrate which is partially wetting by the solvent, what happens is due to in situ dewetting, you get structures which are out of phase with respect to the substrate. Okay. In contrast, if you have a substrate, so this I have decided we talk that in situ dewetting we will be talking later when we discuss dewetting in greater detail. But for the time being, we need to understand that if you have a partially wettable substrate, then by direct spin coating, it is one gets a structure or a film surface which is undulating, but the undulations are out of phase with respect to the bottom substrate. In contrast, if one has a surface substrate which is completely wetted by the solvent, then one still gets a in phase structure. And then a combination of this or these surface undulations, if now one places a stamp like this, which is perpendicular to the direction of the undulations or at 90 degree with the direction of these undulations, then what happens is now there is, you can see very clearly in both the geometries it is valid, that there is a variation in the spatial contact. And now, if you allow CFL to take place, so let me just draw it neatly. So, you have a undulating surface like this, let us say. So, whether which of the geometries you have depends on the wettability, but irrespective of that, if you now bring in a stamp from the top, you can now see that there will be capillary rise only over these areas, because these are the zones only where the film and the stamp are in direct contact. So, this will also lead to structures with 2D order, as there will be a spatial variation in the extent of contact, which will transfer into a spatial variation in the extent of capillary rise. So, today's lecture I will stop here. I gave you some examples where we saw how beyond the master patterns or patterns with complex geometry can be obtained by capillary force lithography using simple stamp in one case, and a combination of a simple grading pattern stamp and a grading pattern substrate in the other case. We will continue our discussion on soft lithography with two more things that are going to come up. One is how to make chemical patterns, that is the micro contact printing in little bit detail, and a couple more examples of beyond the master patterning, where other than creating 2D structures, you control other parameters to make more distinct structures from the original stamp. Thank you.